In today's tutorial, we'll learn how to use the new volumetric raymarching features available in the RayTK Volumes add-on to create transparent clouds of color. We'll be doing this in two parts. In the first part, we're going to use an SDF to create and render a volume. Then, in the second part, we'll take that volume, export it to a 3D texture, apply feedback to it, and then pull it back into RayTK to render. This tutorial depends on having the RayTK Volumes add-on as well as the main RayTK library. There are download links for both of those in the video description. The second part is also going to involve using Joseph Pell's T3D library, but this first video doesn't require it. The first step is to download the main RayTK library from GitHub. Go up to the root of your project outside the main project comp and drag the RayTK tox file into the project. I recommend doing this outside the main project comp because if it's in the same network as your scene, you're going to see a lot of these data connectors, which can be kind of confusing visually. The second step is to get the RayTK Volumes add-on from my Patreon. There's a link to that in the description as well. Drag that tox file into the project next to the RayTK comp, and then go back into the main project comp. Before moving on, it's important to remember to save your file regularly. There are some issues in Touch Designer that can cause crashes when creating RayTK scenes. Those issues should be addressed soon, but it's still a good practice to save often to avoid losing any work. Open the RayTK palette using the Alt-R shortcut and create a Volumetric Raymarch Render 3D. If you don't see that showing up in the list here, it means that you need to load the RayTK Volumes add-on into the project. Drag out of the first output and create a null top so that you can see the rendered image result. To get a nice interactive viewport, we're going to use the camera viewport component. So select the renderer, and then open RayTK's Editor Tools menu with Alt-Shift-R. And then under Add Camera, I'm going to choose Linked Camera. Then on the linked camera, click the Create Camera Viewport button. Then go to the camera page in the parameters on the camera viewport and drag that null top into the render top parameter here. So that's now going to display whatever comes out of the renderer in the viewer of the camera viewport. You can right-click the camera viewport and choose View to pop it open in a window, and then place that somewhere on your screen. But I'm going to be using this panel on the side just to make things fit within the frame for the recording. To define shapes in our scene, we can use an SDF similar to with regular raymarching. Create a torus grid SDF, and then set the axis to Z, and decrease the rows to 4. If you try connecting this to the first input on the renderer, you're going to get an error saying that the input does not support SDFs. Instead, we're going to need to provide it what's called a volume. But before we do that, let's first discuss the difference between volumetric raymarching and regular raymarching with SDFs. Or you can skip ahead to the next section if you don't want to know the theory. In regular raymarching, the renderer steps along rays coming out of the camera and going into the scene. And at each step, it looks at the contents of the scene and finds how close the nearest part is to that location. And then it knows it can step at least that far. And then it repeats the process, getting the new distance for the next step, and so on until it ends up getting so close to a surface that it considers it to be a hit. And then it shades that surface using material. In volumetric raymarching, there are still rays coming out of the camera going into the scene. But rather than looking up distances using an SDF to take steps of different lengths, it just does a bunch of steps that are all the same length. There are two variations of this that are supported by RayTK. There is solid surface and cloud mode. In solid surface mode, at each step as it's going along those rays, it checks to see how much stuff is in that spot within the scene. And if it's dense enough, it considers that to be a surface, and it stops and uses the properties of that surface to shade the pixel. In cloud mode, though, at each step, it checks to see how much stuff is in that spot, and then adds some color to the result, and then takes another step and repeats the process again until it's gone all the way through the scene. And the combined amount of color that each ray picks up along the way is the color that the pixel gets. This approach means that we can use content that doesn't have known surface distances, like data from a 3D texture or a noise function. So instead of a surface distance, we need to know a density. There are a few different operators that allow us to create volumes. In this tutorial, we're just going to cover the one that uses SDFs. So open the palette and create an SDF volume. And then we're going to insert that between the torus grid and that first input on the renderer. It's going to take a second while it compiles, and then once that's done, you can use the interactive viewport of the camera to take a look at what it's showing. So by default, it's in solid mode, so this actually looks basically the same as what you would get with the traditional renderer. So on the renderer, let's switch the March mode from solid surface to cloud. Then go over to the torus grid SDF, and let's make it a little bit larger with a radius of about 1 and a thickness of 0.4. And then you can bring up the bar thickness to maybe 0.15 or so. So now we get a render that is showing all the way through the shape, and in the areas where more of the shape is being hit, it's going to be brighter. So let's leave the camera view off to one side so that you get an angled view there. Next, we can make the SDF a bit more interesting by varying the thickness of that torus. So just going to make some room over here. Select the torus grid SDF and open the Editor Tools menu with Alt-Shift-R. And then under Reference Variable, choose Normalized Angle. This gets us a value that goes from 0 to 1 as the angle goes around the ring of the torus. Then open the palette one more time and create a wave field and connect the variable reference to its first input, the coordinate input. Then just a quick optimization here with the wave field selected, open the Editor Tools with Alt-Shift-R, and under Lock Param, choose Wave. This will bake in that setting into the shader, and it's going to help improve performance later on. Now we can wire up that wave field to the thickness field input on the torus grid SDF. It's going to take a sec while it recompiles, and now we've got one instance of that sine wave going around the curve. So let's get that up to 3, and in the period here we can use an expression 1 divided by 3. So now if we adjust our view, we've got 3 sine waves that are varying it, but the thickness is going all the way down to negative values, which is why things are disappearing on the sides there. Decrease the amplitude to around 0.2, 0.3, something around there. And then bring up the offset a bit to maybe 0.5 3, just so that we get a little bit on the sides there and it's not totally disappearing. Now we can use the phase parameter to shift that expansion and contracting pattern around the ring. We're going to add some animation to this later on. If you try mousing around in the view, you may notice that things get a little bit choppy. It may not come through as well on the video recording, but you should be seeing it a little bit more on your computer. This is happening because the renderer is taking a limited number of steps that are always the same length. So let's go over to the renderer. And we've got this step size parameter here. So if you try bringing that up, you can get it to a point where it's really obvious that you're getting a finite number of slices as it goes through the scene. So one solution to that would be to bring the step size all the way down, and then the steps are going to be so small that we don't really see them. But if you bring it too far down, then things are going to disappear. And that's happening because it's basically running out of steps before it makes it all the way through the shape. So on the settings page here, we have this max steps setting that limits the number of steps, and it's hitting that limit before it goes all the way through. Let's leave that though as it is, because if we have a really large number of steps, then performance is going to get pretty bad. Let's go over back to the first page, and we can try a few different strategies for improving this. Let's bring the step size up to around 0.05 so that you can see it a little bit in there, but it's not really large. To avoid some of the banding that's showing up in here with those slices, we can tell the renderer to offset each ray by a different amount for each pixel. And that means that the rays, the steps along each ray, aren't going to line up in those flat planes there. In future versions of the toolkit, there's going to be a built-in setting in the renderer for this on the settings page, but in this version, we need to give it a field to tell it how to come up with those random offsets. So to do that, we can use a noise field. So open the palette with Alt-R and create a noise field. And then just drag that onto the renderer's ray offset field parameter. Then we've got this offset amount that we can use to scale how much it does that. And if it gets too low, then you're going to see the same banding issue. And if it gets too high, you're going to see some static in the render. So let's just leave that at the default of 0.5. We still have a little bit of banding that's showing up in there, but there are some other strategies that we can use to improve it. Next up, we can adjust how the SDF is being filled to create the volume. So remember from the theory section earlier that volumes are based on density. So let's go over to the SDF volume operator, and we have some settings here that control how it fills the area of this SDF with density. So by default, it's just filling it with a constant density on the inside and then 0 on the outside. Fortunately, it has the blending setting here allows us to smooth out that transition from inside to outside. So if you bring that up a bit, it's going to smooth out those edges. In future versions of the toolkit, there might be an option to have it do that blending kind of coming out from where the surface was originally, but at least in this version, it's always doing it kind of starting at the edge and going inward. So things are going to thin out a little bit when you increase the blending. So let's set that up to around 0.15 or so. And then we can use the offset here to just expand it out a little bit. So go up to maybe 0.04. So now we have a nice soft transition from the inside area to the outside area, and we still have enough thickness that we can actually see the shape. And just by doing that, we've already improved a lot of the remaining banding issues that were showing up in there. After the density, we can move on to color, which is going to be based on a noise pattern. Create an assign color and insert it between the torus grid SDF and the SDF volume. Then create a noise field and this would be a good time to save because we're just about to wire some things in. Then create a spectral color field. And we're going to use this to go from the single number that the noise field provides into color values. So connect the noise field to its wavelength input, and then connect the output of that to the second input on the assigned color. Spectral color field uses whatever wavelength value comes from its input and turns that into a color using a few different techniques. By default, it's expecting that to be in the 0 to 1 range, though if you want to go with nanometers, you can do that if you want to be all sciencey, but let's just leave it at normalized 0 to 1. To get the noise field to produce values in that range, let's go over to that, drop the amplitude down to 0.5, and then bring up the offset to 0.5. So now it's going in a range 0 to 1, and we're getting that full range of the spectrum. You can also try out some of the different spectrum types here. I like the Zucconi 6, but there are a bunch of other options in here that you can try. And remember to save before moving on to the next section. Next, we'll add a bit of twisting to make that shape a little more interesting. So just zooming out the view here to get a wider view. Create an axis rotate and insert that after the assigned color. Then let's give ourselves a little bit of room and create another wave field. And again, select that, open the editor tools with Alt-Shift-R, and then choose lock param wave. And then connect that up to the second input on the axis rotate. As the scene gets more complex, it's going to stall for a little bit longer as it compiles the shader when you wire in new operators. Bring up the amplitude to maybe 15 or so, and then you can bring up the period to maybe 2 to spread it out. You can try different combinations of axes on the wave and on the rotation. I've found that doing rotation around the z-axis with the wave along the y-axis produces some nice results. So now we can try changing the phase, and we get some nice distortion there. We'll animate this momentarily. So remember to save the file, and the last part is going to be adding the animation. We're going to do this in 4 places. We'll start over on the SDF and the wave field that's controlling the thickness of the ring. Select that wave field and open the editor tools with Alt-Shift-R. And then under Animate with Speed, I'm going to choose Phase. Then on the speed generator, you can adjust the settings here to control how fast it's shifting around the ring. And then you can use the speed setting here to kind of give it a range, and then use the slider to provide easier control over it. I'm going to slow that down a little bit. Then select the torus grid SDF and try changing the shift parameter here, and that's going to shift the rows and columns of that grid around the torus. So select the torus grid SDF, open the editor tools with Alt-Shift-R, and then under Animate with Speed, choose Shift. On this one, we have two different parts that we can control. So on the speed generator, you can change the values there to get it going faster in one direction or the other. You can use the reverse to have it go the opposite direction, and then use the slider to control the overall speed. Then let's head over to our noise field. And we're going to select the noise field, open the editor tools with Alt-Shift-R, and under Animate Speed, choose Translate. So in this one, the type of noise that we initially selected is only using the X and the Y axes. So let's go to the noise field and switch that to maybe simplex 3D or even 4D if you want. That's going to take a second to recompile. And then we can get to adjusting the speed on the different axes, get it to maybe move a little bit faster on the Z axis, slower on the Y, and so on. And then use that slider to control the overall motion. And let's also just, on the noise field, bring up that scale to spread out the pattern a bit, so maybe like 2.5. Then let's go over to the twist, where we have that other wave field, so select that, open the editor tools with Alt-Shift-R, and then under Animate Speed, choose Phase. And then again, you can dial in the speed settings here however you like. And that's it for this video. So remember to save your file. And to recap, we are creating a shape using an SDF, a torus grid SDF. We are using a wave field with a variable reference to vary the thickness around the ring. Then we're using a noise field to derive a spectral color that's being assigned to that SDF. Then we're doing some twisting with an axis rotate in the wave field. And then finally, we convert to a volume, and we use the blending setting here to smooth out that transition on the edge. Then we are rendering that with the Volumetric Raymarching renderer, and that's in cloud mode. And we're using the noise field here to offset the rays to help improve the banding that shows up in the renderer without making the step size too small, which would have an impact on performance. There are lots of things that you can do from here, but one thing to note is that at least in this version of Touch Designer, there is an issue that can cause it to crash if you insert too many RayTK operators into the same network. For some reason, I found that trying to add another rotate operator at the end of this chain seems to pretty reliably cause that to happen, so I would avoid doing that and just make sure it's saved before you wire anything new in. Derivative has a fix for that issue, which is going to be included in an upcoming Touch Designer release, but until then, it's just important to save your file. Good advice in general. As long as you're careful, though, there are lots of things that you could change in here, like swapping in different kinds of SDFs, or using a different type of pattern to assign colors, or different types of distortions there. Lots of options. You can even use a field to control the density, so it's different in different parts of the shape, using that input on the SDF volume operator. In the next video, we're going to take this scene and export the density out to a 3D texture so that we can apply feedback trails to it. And then we're going to pull that back into RayTK to do volumetric rendering. If you're watching this, you're probably already subscribed on Patreon, but if not, consider signing up. You'll get early tutorial access, exclusive downloads, Discord community access, and a bunch of other stuff. Anyways, thanks for watching, and make sure to like and subscribe.